Welcome back to Scary Programming Terms. The topic this time is lazy evaluation. So this used to be an idea that was the domain of weird functional languages like Haskell, but it has crept into mainstream languages all over the place, like C# and Java. In C#, the main way people use it is with a library called link. And people use this all the time in C#, and not everyone's even aware that they're using lazy evaluation when they use it. So here's a little example. We have an array of numbers, 1 through 10. And we want to find only the even numbers. So there's this link function called where, and you provide it a predicate, which is just a function that returns true or false. And so by telling it we only want values x, where x mod 2 is 0, so we only want even numbers. Then here we get the squared numbers. So select lets us do a transformation, so every x we square it. In most other languages, this function would be called filter. This one would be called map. Just something to think about. And then finally, we say we want the sum of the numbers. So lazy evaluation is happening here. So what does that mean? So this where statement that only gives us back even numbers is not actually giving us back an array of numbers or anything. If we look at the type here, we see that we have a enumerable of int. Right? An enumerable is just an interface. So what have we really gotten back here? So it turns out that this doesn't really, by itself, do much of anything. In fact, no matter how big of an array we passed to this where statement, it would return almost instantly and give us this variable even numbers. So what is it actually doing? Well, what's kind of cool is we can actually go look at the source of this. This is the actual source code for link. And this is the where function. So the where function is an extension method for other enumerables. An array can be treated as an enumerable. So our array is the source in this case. And this func variable is the predicate. That's the function that says true or false. All right, so there's a lot of error checking. Make sure source isn't null, predicate's not null, and so on. And then basically we just return a where enumerable iterator with our source, in this case the array, and with the predicate in it. So what is a where enumerable iterator? Let's go look. Where enumerable, find the next one. Okay, so this is the where enumerable iterator, and it's got a source enumerable. Right, that'll be our array in this case. And it's got the predicate, and then another enumerator here. So what does it actually do? So it is itself an iterator. And iterators are things where you can move from one value to the next. And so here is the move next value. And what does it do? Well, it just takes our enumerator, which we get from the source, and it moves to the next value. And then it checks that value and says, does the predicate match it? And if so, it sets the current value to that item and returns true. All right, so it says we successfully moved to the next, and here's the current item. If the predicate is not true for that item, then we just skip and move to the next thing. So what will happen if we were to call move next on even numbers, right? We could do that. What do we need to do? Let's see, what does enumerable give us? So behind the scenes, we know it is a where enumerable, but we only get the IEnumerable interface, which okay, so we have to say get enumerator and then we can say move next, right? So if we keep calling that repeatedly, we're going to get only the even numbers as a result. It's going to iterate across the whole array, but our move next will only return 2, 4, 6, 8, and so on, right? It's going to skip over the 1 and 3 because they don't satisfy the predicate. Right, so that's what move next will do. But at this point, we haven't called move next, right? All we've done is gotten back our where enumerable iterator. Okay, so now we're going to take that where enumerable iterator and we're going to call select on it with this function, x times x. So what does select do? So again, we can look at the source. Here is select. Takes in our source enumerable and our selector function. And it's basically exactly the same as where. Right? It doesn't do anything, checks for some errors. Nothing actually happens except now we get a new iterator, the select enumerable iterator. And it has the same structure as the where enumerable iterator, right? It's got the source, the selector, a function, and an enumerator. And it has a move next function. And so that move next function calls its sources enumerator and applies the selector to every item it gets as it moves next. So in this case, that doesn't skip any, right? It's not checking to see if the predicate is true. It's calling the selector every time. And then finally, we're going to call sum. And so sum is a different case. We should be able to check that source as well, if it's in a normal place. Yeah. So what does sum do? Sum just iterates through the iterator, right? For each is calling move next behind the scenes, basically, and getting a sum. Sum plus equal value. So nothing actually happens here until we call sum. And that is the idea behind lazy evaluation, right? We tell C# that we want only the even numbers. And we tell it we want to square all of the even numbers. But it doesn't actually do it until we somehow request some work actually be done. Right? No work needs to be done here. No work needs to be done here. Once we want a sum, now we need to do work. So now we're going to be behind the scenes calling move next, move next, move next, and getting the result. So why is that actually useful? So one reason it's useful is we don't want to iterate through this array multiple times to do what we've asked of it here, right? So if we were to get an actual list of numbers here, which we could say to array, and we get back an array of even numbers, right? So we would iterate over this whole thing and get only the even numbers. And then we'd have to iterate over the whole thing again to square each number, right? And if that gave us back an array, then we'd have to iterate over the whole thing a third time to sum each number and get the total, right? And that could potentially be inefficient, and we're allocating multiple arrays, right? We're allocating this array, and the even number array, and then the squared numbers array, and iterating it over 3 times. By using lazy evaluation, we can express this like so, and this does not get iterated over at all until the end. So it gets iterated over only once, and we're not allocating any new arrays at all, right? Because all we've asked for here is a sum, which is a single value, so we don't need to allocate any new arrays. So that is the usefulness of lazy evaluation. And this can become even more important if our source is not an array, but say it's a file or a network connection. where all the data might not even be available yet, or it could be very slow, and so you definitely don't want to iterate over it multiple times. Now, an important thing to remember about lazy evaluation is that there is a cost to this, right? When we look at this code, say for summing, right? This for each is having to call that move next, and that move next is going through a whole chain of calls, right? It's having to call move next on the squared numbers source, which calls move next on the even numbers source, which calls move next on the array. So there is some runtime overhead, at least in C#. Some languages are able to compile all this kind of stuff away. The Java Streams library, for instance, and Rust do a better job of compiling away that inefficiency. But in C# there is some overhead here. So it's important to understand how your language or how your library does its lazy evaluation to decide if that cost is worth it. So for instance, if you're working with arrays, to do a job like this, where you're just working with numbers and summing them up, this can have quite a lot of overhead. And especially if you just do something like this. Like this is very convenient in C# to just call sum to add up a bunch of numbers. But it is much, much slower than just doing a for loop. Right, something like this. This actually turns out to be much, much faster than this, which is unfortunate because this is so convenient. But there's nothing stopping you, if you don't need lazy evaluation, from making similar convenience functions like sum that are implemented this way rather than with iterators or enumerables. And so there's libraries like pulling one up here. So this is one I made. So this has similar functions to link, but does not use lazy evaluation. Now that can be very good if you're just doing something like summing or averaging an array or getting the minimum or maximum value of an array. And you can see some benchmarks here. So like if you use link with the lazy evaluation stuff to get the minimum number from an array, you can see that average time here is 548 microseconds versus the link faster version, which just uses a for loop, which can do it in 69 microseconds, right? 10 times faster. And also there's no allocation, right? Link has a little bit of allocation overhead. It's very small though and short-lived, so it's not really much of a problem most of the time. And then I have a SIMD version that goes even faster, right? So that's good, but it could also be really bad, right? If you were to do a big chain of things, like we had before, right? If you did this with link faster, it could be a lot slower because you're allocating multiple arrays each time and iterating over the thing multiple times, right? So you have to think about whether lazy evaluation is appropriate for what you're doing. Sometimes it can be a really big win, especially when you're working with like file or network I/O, or if you're chaining lots of things together, right? If you're chaining lots of wheres and selects and other operations together, you could express it in a much less code than you could with a for loop and be much more likely to get things correct than having a bunch of nested for loops, for instance. But if you're doing something really simple like this, maybe it's not worth the overhead to use something like link. And again, every language is different, so it's important to understand how your lazy evaluation library works to get good performance out of it. Any questions about this? Feel free to hit me up in chat. And if you find this concept of lazy evaluation interesting, it's worth playing with Haskell because the whole language is built around this idea. And because the whole language is built around it, it can do pretty interesting optimizations with lazy evaluation as well. All right, looks like no questions. So I'm going to sign off and I'll be back later. Thank you.